and so he's a computer scientist, AI researcher, and obtained his PhD degree at University of Illinois, in Champaign, in 2007, and then he built a career as a postdoc and a faculty member at Virginia Tech University until 2018. So he's a real multidisciplinary researcher working mainly on agent-based modeling, simulations, but he's very much interested also in all kinds of AI application, machine learning, and his agent-based modeling expertise has been applied in many domains like epidemiology, climate changes, and so he collaborates also with those kind of scientists, mathematicians, and statisticians. And so his work has been also appreciated and awarded many times. And we know each other from multi-agent system communities, and a special track or attention of these communities on agent-based modeling and building large-scale multi-agent systems. So thank you for also what we're prepared to come and visit us in this difficult time, and we had a very nice week, and we had several meetings, collaboration, so it was very nice, and may I ask you to come and take the floor?
Yes, thank you very much.
Thank you. Thank you.
Thank you, Mehdi, for the introduction. Thank you all for coming here to the talk. And thank you for arranging the beautiful weather for my visit. Appreciate it. I'm going to talk about agent-based simulations for disaster preparedness. And I want to start by acknowledging all my colleagues at the University of Virginia. I work with a very large group of people, other faculty and research scientists and postdocs, and they're really from many different disciplines. So they're economists and statisticians and epidemiologists and physicists and so forth. And we really believe in team science. So we think that by working together, we're able to address much larger problems than we can individually. So collaboration and team science really are our driving philosophies. And this is just sort of a representation of a general approach to things that we have, which is that we take data, as much detailed data as we can get. So for example, there's population information from places like the census, there's geographical information about activities that people do. And we try to integrate it all. And these result in like digital twins or synthetic populations, very detailed representations of real people and real places. And we construct these synthetic populations that show, where people live and where they might move around, where they might interact with other people and so forth. And from these, we can extract other representations that are useful, like network-based representations. So if you think about an epidemic, it spreads over a network of people coming into contact through co-location, right? So we can build those kinds of representations and compute with them. And we build a lot of tools to doing those kinds of computations. So we need tools for visualization, for simulation, for analysis. And we then apply it to a range of different domains. So for example, we've been working on COVID, like Mehdi said, but we've been doing computational epidemiology for many years. So this is like a joke about swine flu, which was in 2009. If you have kids, don't tell them not to do that. And we've also applied it to climate change type things, so extreme heat exposure, to disasters. This is sort of a notional disaster, which is a nuclear device going off in Washington, DC. And this is Hurricane Harvey, which I'll mostly talk about today. So let me just tell you, because this is more broadly about disasters, let me tell you about some of the different kinds of disasters we've worked on. So computational epidemiology is a big area of work for us. We've worked in this area for several years. Some of my work has been around what are good vaccination strategies, what are economic impacts, urban-rural differences in epidemics, localized interventions. So we've seen, of course, with the pandemic that you really need to intervene everywhere. But often, where you focus your intervention can make a big difference. So that's what is meant by localized intervention. So this picture, some of you may know what it is. It's a map created by the first epidemiologist, a man named John Snow, in 1854, was studying a cholera outbreak in London, in a district called Soho. At that time, there even wasn't a germ theory of disease, so we didn't know what causes something like cholera. And so he had a really holistic approach. He made a map, and he plotted all the cases. And he visited people and talked to them about what they did, what kind of activities they did, and where they went, and who they interacted with, and so forth, right? And from this, he was able to infer what the most probable cause of the disease was. Cholera is a waterborne disease, so it was spreading through tainted water. And there was a particular pump here on Broad Street, which he sort of zeroed in on by looking at the distribution of cases. They said it's clustered more over there. And so he was able to figure out how to stop the spread of the cholera outbreak by basically, they say he took the handle off the pump, so nobody could use it anymore. But what I want to point out is that the kind of information he's relying on here is information about location and mobility and interaction and travel and things like that, which is exactly what we still do today, right? So now we can get mobility data that's global, let's say from location and mobility data from cell phones and things like that. So this is actual mobility data from one of these companies that tracks people's locations from their cell phones, right? And this is representing some 20 million people globally, and you can get all kinds of information here. So for example, there are a lot of people in the ocean on ships. There's a person on the flight who forgot to turn off his phone. And then, there are all the people moving around in their normal daily activity patterns. So there's, much better information available now. And the other thing we can do is we can make these synthetic populations. So we can have sort of a rigorous computable representation of who people are and where they might live and where they go and so forth. And one of the challenges, of course, is to do this in a rigorous way, but also in a privacy-preserving way. So we want, for example, to be able to do these computations without being, saying something like, oh, you have to change your behavior, right? It has to be sort of more general than that. And one of the things we do is we take, let's say, demographic information from one source and information about activities from another source and information about locations from another source, and we integrate them in ways that represent typical patterns in the population, right? So it's not the linkage. It's not like this person in the demographic data is exactly this person in the activity data, but we try to match them in reasonable ways so that the resulting representation is meaningful, but also somehow preserves privacy, right? And I just want to call out this work with Mehdi and others here at Utrecht. So in computational epidemiology, one of the challenges has been how to integrate models of human behavior. What do people do and why do they do it, and how will they respond to interventions and so forth. And there's a well-developed modeling methodology in multi-agent systems called the belief, desire, intention model, right? And so, but those are complex models. They're computationally intensive. So if you try to put those kinds of models into simulations, then it becomes a challenge to scale them to large numbers of agents. So that's something we've been working on together. And then it allows things like normative reasoning. So we have interventions, and they tell you you should wear a mask, right? So that's a normative thing. And people look around and see, are other people wearing masks? Maybe if nobody else is, then I don't need to either. That's another normative thing. That's called a descriptive norm, right? So we need to be able to do this kind of normative reasoning in order to be able to build good models of human behavior in these simulations. So that's another goal for our project. And once we can do that, then we can talk about optimizing interventions. So we say certain interventions were carried out, could they have been done better, right? Can we find interventions that are fair and equitable in some sense? So those kinds of questions are very interesting to us. That's what we've been working on together. I think it's going in a very interesting direction. We have a couple of papers about it already. And I think this will be recorded. The talk is recorded, so you can find those later. Another kind of disaster that we worked on several years ago now, this was in 2013, it's called National Planning Scenario 1, NPS1, in the United States. So the Department of Defense in the US has a list of national planning scenarios. There are like 13 of them. They're all different. But the first one on the list, this is surprising, at least to me, is that an improvised nuclear device goes off in Washington, D.C., right behind the White House. So the White House is here. This is where it notionally goes off. And what would happen? So it turns out they've been studying this since the beginning of the Cold War, not surprisingly. So there are a lot of detailed physical calculations that have been done. They know, where all the big stone buildings are and where all the glass is and what will fall down and what will not, and how the radiation spread and the thermal fluence and the fallout, which direction will it go, all those kinds of things have been worked out. Right? But when they talked to us, they said, we don't know what people will do. Okay? So to them, right, in their physical calculations, people are bags of salt and water that sit in one place, and they accumulate radiation, and they say, okay, after 20 days, this is how much radiation you'll have been exposed to. Of course, nobody's going to sit in one place, right? People are going to move around and try to find their family members, try to leave the area, try to seek shelter or healthcare, or who knows, all kinds of things, right? And so they said, you have this synthetic population. Can you figure out something here? Can you model this? So that was the effort here. There are a number of other papers, but this is one of them. And we looked at what kinds of interventions might have low cost in the sense of being easy to implement, because this is like not a place you could go after an improvised nuclear device goes off. So you have to be able to do something remotely, but still help people, right? And so one of the interventions was trying to restore communications. And that can be done by, for example, bringing in cells on wheels or having some balloons or drones or things like that. And restoring communication gives people options, right? It lets people interact, get information, react, and adapt. So it can save lives. So this work, because it was a big and complicated simulation, led to also a stream of work in what we call simulation analytics. Because when we have a really big simulation, and it's got a lot of data and hundreds of thousands or millions of agents in it doing complicated things, even saying, you run the simulation, you get more data than you started with. And so just saying, well, what happened? That's a difficult question to answer, right? So that's what simulation summarization is about, for example. Can you extract sort of a summary representation from the simulation that tells you what happened and perhaps why it happened, and that you can query, for example. Right? So that was one. The thing was about taxonomy generation. So if you think about responders, first responders in many emergency situations, they're trained using certain kinds of taxonomies, right? So they have these ideas about, you'll find people who are running towards the disaster rather than running away from it, right? You'll find that people who have survived try to help people who are hurt. So there's this sort of taxonomy that they have about what people do in these circumstances and where and why and so forth. And they use that for training. They use that for preparedness. Right? So we can ask, well, can we take a simulation like this and generate a more sort of more data-driven taxonomy that can be used for training first responders? Right? How do you do that? How do you take an agent-based simulation and do that kind of taxonomy generation? That's that paper. And then the kinds of questions people have is, okay, so I'm trying to respond to this event. Tell me what people should be doing. Right? So that's like a query. Like somebody might say, well, what should people be doing 1 hour after the bomb goes off? Right? What's the best thing to do? And it turns out that there isn't a single answer, because everybody shouldn't be doing the same thing. If you're close to where it was, then you should evacuate. And if you're far away and out of the path of the fallout, then you should shelter. And things like that are different. And so it depends on the context of the person. And so you have to be able to find a recommendation for what somebody should be doing that is sensitive to their context. Right? But we don't know what the right contexts are. Right? And so the challenge is, if somebody gives you something like a partial context saying 1 hour after the bomb went off, that's already specifying part of a context. Can you then expand that and say 1 hour after the bomb goes off, if you're in this situation, you should be doing this. And if you're in that situation, you should be doing that. So you need a method that can intelligently discover these contexts from a simulation and come up with behavioral recommendations. So that's that. And there are other things. I just thought I'd highlight a few to tell you about the interesting technical work that comes out of some of these agent-based simulations. Okay, so the thing I'm going to talk about today mostly is a hurricane. It's called Hurricane Harvey. And this is the Gulf Coast of the United States. So this is the city of Houston, which we'll be talking about mostly today. And it's in the state of Texas. And it was a huge hurricane. It really dumped a lot of rain on this area. And there was a very extensive flooding. And what we have been doing, with thanks to a grant from NASA, is trying to understand social vulnerability. So NASA has a lot of satellites that do Earth observations. They make regular sweeps over the Earth, and they record many things like temperature and rainfall and pressure and all kinds of things, flooding and particulate matter, right? And they make these observations available to anybody who wants to use them. It's taxpayer funded, it's open. But what they want to do is they want to encourage people to make use of these data in different applications. Right? So they have a program in health and air quality, which is what our grant is from, where they would like to see these Earth observations data being used to understand something about human health. Right? And so our particular project has to do with social vulnerability in or during disasters. So the CDC in the US, the Centers for Disease Control and Prevention, one of the groups there has come up with something called a social vulnerability index. Right? So that says it's a region-specific thing. So they say, based on the demographics of the people in the region, can we ascribe some notion of vulnerability to them? And that's what they came up with. This was in 2011. This is a map showing at the census tract level differences in social vulnerability. Okay. And what is it for and how is it computed? So it is calculated from census variables, and it is defined at the census tract level. So the geography in the United States is that you have the country, which is divided into states. States are divided into counties. Counties are divided into tracts, tracts into block groups, and then blocks. So census tract is a fairly small region. It has about 4,000 people on average, but it can range from 1,200 to 8,000 according to their definition. Okay. So you have good demographic data available at the tract level, reliable sort of statistics. So from that, they compute a social vulnerability index, and this is exactly what it is. It has 4 themes. So there's a socioeconomic theme, a household composition theme, one about minority status or language, and one about housing type and transportation. And these are the variables that they use. So you can, don't have to go through all of them. But for example, the socioeconomic theme is looking at percentile percentage of civilian or of poverty and unemployment and per capita income and education. So having no high school diploma. So those are the 4 variables that go into their socioeconomic theme of social vulnerability. And they calculate these percentiles over a region. So for example, we say the state of Texas, there are so many census tracts in it. We can calculate the percentiles for each census tract, and we get a ranking from it. And that's the social vulnerability ranking. That's the index. Okay. And there are 4 such themes. And it's really, as far as I know, it's based on sort of expert understanding. It's not based on data. It's not meant for any specific outcomes. It's meant to be a broad thing that's easy to understand, easy to calculate, and can be used in a variety of different contexts. But it is static, right? So it is calculated. It's only updated if there's a change to the census data, which happens every couple of years, so they can recalculate it. But other than that, it is static. It is not based on people's movements. It is not based on what people do during a disaster or anything like that. Okay. There can still be a substantial amount of variability. So this is like one area with multiple census tracts in it. And you can see the differences in the patterns of the vulnerability due to the 4 different indices. So you can just see that different areas are light and dark in the different maps. Right. And this is just from their website. It says this is what they use the SVI for. So amount of needed supplies, emergency personnel, emergency shelters, best ways to evacuate people, and who will need support, who will need more support to recover following an emergency or natural disaster. So really, it is intended for use during natural disasters also, even though it is based on some static variables. So one thing we can do, of course, is we can make a dynamic version of it using a synthetic population, because people move around just in their typical, daily or weekly activities. People move around, and census tracts are fairly small areas, so people travel outside their census tracts all the time. Right? And so you would expect that the vulnerability associated with the region, since it's tied to people, depends on the people who are there at that time. Right? So you can make a dynamic notion of social vulnerability based on people's normal movements, and we have used a synthetic population to model these changes over the course of a week. So this is just showing the first theme, and this is the static version. This is the dynamic version. If you look closely, you can see there are some changes happening. And this shows the correlation between the static and the dynamic version. So you can see at nighttime, there's higher correlation because most people tend to be home, not everybody all the time, right? And then during the daytime, the correlation drops, then it goes back and drops and goes back. So over the course of a week, it changes quite a bit. On the weekends, it doesn't drop as much. Maybe people don't travel as far. And here you can see the changing correlation. So you can see that as the days or weeks go by, there's a lot of variability also. So this is the dynamic SVI on the x-axis and the static SVI on the y-axis. So you can see there are points off the diagonal quite a bit. So there's quite a bit of variability that emerges. Right? So we're currently validating this using EMS data, which is emergency medical services. So when people need to, maybe somebody has an accident or a cardiac event or something like that, for which they need to call emergency medical services, then we actually know, it's not tied to their home location. We say it happened while this person was over here, right? And so if people move around in such a way that vulnerability shifts, then perhaps we should be able to predict it better using a dynamic notion of vulnerability than just a static notion tied to people's home locations. Okay. So this is based on people's normal movements during a week. But of course, during disasters, mobility is not typical. Right? People do very different things. They don't just go to work and go to school and so forth. So let's look at Hurricane Harvey. Okay, so here are some statistics about Hurricane Harvey. It started out, I think, as a Category 4 hurricane. And these categories have to do with wind speed. By the time it hit land, it had been downgraded to a tropical storm, which sounds less threatening, but it just means that the winds weren't as strong. It came over land, and it sort of stalled over there, and it just poured. It delivered a huge amount of rainfall, over 100 centimeters of rainfall over the course of 2 or 3 days. So it's like this much water everywhere all of a sudden, right? And of course, everything was overwhelmed, right? So power systems and drainage systems and transportation systems, everything was completely overwhelmed. A lot of people evacuated, more people sheltered. There was a huge amount of damage. A lot of people had to be rescued. There were, people who had boats were out there rescuing people, and 1 million or so vehicles are ruined beyond repair and so forth. So one question we have is, well, how does this affect vulnerability? Right? What do people do in such a situation, and how does that change their vulnerability? For example, people have flooding exposure, right? So for example, people are trying to evacuate, and maybe some roads are already flooded, and so they're exposed to flooding, and they can drown, or they can get some kinds of diseases. They can be exposed to toxicants, so some kind of chemicals and so forth. So how does the process of evacuation affect their exposure and affect their vulnerability, affect outcomes for them, right? So this is showing actually something from our simulation. It's showing our vehicles that are evacuating on August 28th, which was one of the days of the hurricane. And it's showing, how they pass through flooded areas. So it's showing some of the flooding here, some of the flooding here, some over here. And as the cars move, they have to pass through flooded areas, so we can calculate their exposure and try to compare it with the health outcome data. Right? So that's the kind of thing we're going to do here. So we built a simulation to do this. This is showing one of the outcomes from the simulation. The simulation itself works like this. There are a a number of modules to the simulation that coordinate through a database. So we have a module about transportation and one about behavior and so forth, and they run in a specified sequence. There's a control system that's responsible for coordinating the actions of all these simulations, of all these modules, and keeping track of the data being put into the database, whether things are running correctly or not, and so forth. So that's the coordinator. Right? And this is just a sort of general architecture for simulations that we have come up with. And it has a couple of advantages. One is that each of these modules can be developed relatively independently. So it makes it easier for multiple people to work together. Maybe somebody has expertise in transportation and somebody else has expertise in behavior. So long as the interfaces are well specified, it makes it easy for people to coordinate. And then having a database with tables in it for storing the data from each step of the simulation makes it really easy to have data that you can analyze afterwards and see exactly what happened in the simulation. To debug it, to analyze it, all of that, right? So this is this architecture we came up with when we were doing our NPS-1 simulation, the nuclear detonation one, and we continue to use this for new ones. It also makes it quick to develop something and test it, because once you have the architecture, that part you don't have to do again. And it includes things like a simple staging module, which copies all the relevant data to the right places, make sure that the environmental data are updated for the time that you're supposed to be simulating. Then it calls each of the modules when they're supposed to be called, make sure that they run correctly, and so forth. Here's the behavior module. So right now, we're only looking at evacuation behavior. And evacuation behavior has been well studied for Hurricane Harvey. So this is from a paper in Science Advances, where they looked at cell phone-based mobility data to understand how many people evacuated from each census tract and when. And they fitted a model to it also. This is a Cox proportional hazards model. This is their model. Some of the variables that they used to fit were things like when there was a hurricane watch, when there was a hurricane warning. Those are two technically different things. Same thing with tropical storm watch, tropical storm warning. How far is the tract from the coast? What is its elevation? So likelihood of flooding. And is it rural? What is the average age and other demographic things? So they were able to fit it fairly well and come up with a model that explained when people left their homes to evacuate. Okay, so we just used that. And then the other thing was the transportation module. So we developed this ourselves. The student, Qazi Ashik Islam, he did most of the work on this. And this is basically, it takes the location data, which includes flooding and rainfall and road closures and such, and household data, current location, whether they're evacuating or not, where they're heading, and so forth. And it updates the road states. So roads might be closed due to flooding, for example, or they might have reduced capacity. And it calculates routes for evacuating households. In fact, we can pre-compute this if we know their destination. But if it has to be updated during the course of the simulation, because let's say some road that was available earlier is not anymore, then this module is responsible for doing that. And then it moves the households along the roads as they're evacuating. And from that, we can store the data and calculate their exposure. And so, right? So it's a queuing-based simulator. Each household has a pre-planned route to their respective destination. And at the start of each tick, routes are recalculated because, like I said, the road network might have changed. A little more detail. So queuing-based simulators don't strictly model physical space. So it says each road segment, right? So a long road can be divided into segments. Each road segment is a queue with a certain capacity, and cars come and get added to the queue. And then you compute how much time they'll have to spend there to transition to the next segment of the queue, or the next segment of the road. And I won't go into a lot of detail on that, but there was a paper that I had listed on the previous one. So you can look into the details there if you're interested. So we have behaviors. We have behaviors that say when people will evacuate. So it's quite limited. And we have our traffic simulation. And we have all the environmental data about rainfall and flooding and we put it all together to calculate the exposures of people. And then the question was, how do we validate what's coming out of the simulation? And one of my colleagues, Julia Golke, she's at Virginia Tech, and her student Balaji Ramesh, they had data from emergency department visits in Texas, and this data set was only accessed by them. So this was, in fact, in their institutional review board protocol. Nobody else could look at it. So we used this data set to validate the measures that were coming out of our simulation. So the idea was that if our simulation helps to predict some of the emergency department visit data, then we've done something meaningful. And these data should not go into the simulation in any form, just to be sure that we're doing sort of rigorous independent validation. So it was nice that we were forced to be limited in this way, that only they could look at it, and they did not work on the simulation itself. Right? So some of us built the simulation, some of us validated it. We also had a paper about analyzing the emergency department visit data that looks at flooding, but only flooding, static flooding, and sees whether the extent of flooding in census tracts combined with demographic information and things like that can help explain the emergency department visits. So I'll describe that in a moment. Okay. So I apologize, lots of numbers, but I just thought I'd show what the results are. So first, we say, can the SVI by itself explain the emergency department visit data? And so we use what's called a controlled before-after study design, which means we have a control group, and we define distinct periods. In this case, there are 3 periods. There's before flooding, during the flooding, and post-flooding. Okay? And we compare the rates of visits to the emergency department for various causes, overall and for various causes. And we see if a model based on SVI, how well can it explain those visit counts. So it tells us something. It doesn't tell us a whole lot here, but it says that SVI alone can help fit the post-flood data, and it shows the relative rate ratio, which is that more people, as vulnerability increases, you will see more people going to emergency departments in the post-flood period. So that's roughly what it tells us. We can break it down by themes, and we see that the only ones that are significant are theme 2, which is the I've already forgotten. So it's the theme with the first one is the socioeconomic theme. The second one is the one that has the age and education and things like that in it. So I'll tell you in a moment because it's in the next slide. But that one is significant during the flood period. Theme 3, which is the minority status and language one, is significant during the post-flood period. And these effect sizes are there, but they're relatively small. And theme 4, which has the housing and transportation variables in it, is for the post-flood. Now, when we take the SVI and we add to it simulation variables, and in this case, the simulation variables are flood duration along the evacuation route that somebody is exposed to, and it's aggregated for the census tract, and the proportion of the population that evacuated from that census tract. Then we get a better fit, substantially better fit. It's significant for all the periods overall. And in these cases, it is still significant for the same 3 things, but the magnitude of the effect size is much bigger, right? And you can also see the AIC, which is the Kaike information criterion. It goes down, so that means it's a better fit. Yes. Yeah, I mean, you can, only read so much into p-values. It's generally that if it's below 0.05, it is a significant effect. So those are I've put in bold, the ones that were significant. And the other ones for which the p-value is more than 0.05, our model isn't predicting anything very useful. Right, but they're insignificant. I don't know if there is an explanation. I think that they're not very significant in either case. So I don't know if you can read much into the fact that one is bigger than the other.
Model, but still, I would expect, I mean, different, right? Maybe how come this is so?
Right. Yeah. It's and in fact, most of them are similar, except this one again. This is bigger, and this one, like you pointed out, right? So this one in particular is bigger. So that'd be worth looking into, perhaps. Okay. But I think on the whole, it's good news that with the simulation variables in there, we can get stronger effect sizes and get more significance in many cases, right? And the other thing is, one might wonder that, well, okay, you put in simulation variables, but how much is that really due to the flood duration during evacuation? Maybe it's just the flooding. Maybe it's just the flooding that explains it, right? And so, like I said in the previous slide, we had built a model that looks at just the flooding and some demographic variables and tries to explain the ED visits. And so we treat that as our base model here. And then we say, can we improve the fit over that by adding in the exposure during evacuation? And we also get an improvement over that. It is a smaller improvement, as you might expect, but that's the baseline model. And you can see the AIC, it increases when you add the proportion evacuating from each track. And the fit, again, increases if you add the flood duration, so the exposure along the evacuation route and the evacuation proportion. Okay, so the simulation is, the dynamics of the simulation is contributing to something more beyond just the information about the environmental conditions. Okay, and the other thing I want to point out is that there was no calibration, right? So we didn't try to calibrate the evacuation model in any way. We just used the data we had about evacuation proportions from each region, and we just tried to choose reasonable evacuation destinations. And we said, okay, let's see how much exposure there is and whether that tells us anything meaningful. So it's very encouraging that already we have results that show that the simulation tells you something more than you could get just by looking at the environmental data and gross population census or demographics. So what can we do? For example, we can augment the SVI with this. That was the original purpose. So if you look at the SVI as a whole, combined all four themes, this is what it looks like. And if you look at the flooding exposure, it's almost like an inverse of that picture. Right? So here, with the dark, it's the higher vulnerability. Here, those areas are relatively light because there wasn't that much flooding on those days, at least, in the core of the city. So you can combine those things in a very naive way, like the SVI just adds up those four themes, and we can add up the fifth theme also, which is the flooding exposure, and it changes the picture a little bit, right? So that's one way of adjusting the SVI. Better way would be to figure out how to weight them appropriately, right? And so that's something we're working on. We're currently working on learning outcome-specific vulnerability indices from the data. So using machine learning methods. With a different data set, we have actually very encouraging results for that, but I won't be going into that today. So I just want to acknowledge the contributors to this work. So Anna Brower is an undergraduate student. She has really done a lot of work on this. Ashik Islam is a graduate student. And then the others are my colleagues. They're all faculty members. At Johns Hopkins University, Bianca Corpus is a student, and Ben Zajcik is a meteorologist. And at Virginia Tech, I already mentioned, Julia Golke is an environmental epidemiologist, and Balaji Ramesh is a student. And that's really all I have. I've really enjoyed my time in Utrecht, as you can see. So thank you very much for inviting me here.
Yes, yes. The question, which is the role of the cost proportional model in your other process? So,
Right.
how does it depend on the variation of the cost? Like the tester, if you some different assumptions or different models, it will change or does it have any?
Right. So it is a model from the literature. It's published in a very reputable place. So I don't have much issue to take with that. I think in the last set of simulations we did, actually, we just replaced that with data about the proportions of people who are evacuating from each census tract.
That point processes or just,
So literally just, we're saying that on each day, a certain number of households have to leave a census tract, and we just use the data on how many people left on that day. Yeah.
Yeah, because it's some kind of constraint, some parametric. This way you do like a, understand well a non-parametric estimator of this item. Yeah.
So I don't know the short answer, but it is useful to have a model like this, or maybe a non-parametric one, if you want to go beyond the days for which you have data. But since we are limiting ourselves to the days for which we had the data, we just use the raw numbers or raw proportions. Yeah.
How is the vulnerability index defined, or what does it really capture, or in what way does disaster affect it? Because it makes sense of the indicator that you're looking at the effect on.
So you're saying how we augmented it, right? So we're just saying at this point that we can have another theme, like there's a socioeconomic theme and so forth. There's an exposure theme, which is you aggregate the flooding exposure for everybody in that census tract and assign it to them. Everybody who originates from that census tract. Yeah.
The models, they depend on the kind of disasters you're looking at, like flooding or prepared things with probably having different evacuation structures, right?
Exactly. So part of the claim here is that we have a methodology and we have tools that we can build to study a different disaster, let's say a hurricane in a different area or a completely different kind of disaster, and construct a vulnerability index or an augmentation of vulnerability index for that disaster for that area. So it has to be, my feeling is that these vulnerability indices need to be made more hazard specific and outcome specific. Very general vulnerability indices, though they're easy to understand and everybody can use them, tend not to have very much value in terms of actual predictability of outcomes.
I had a question about the dynamic social vulnerability index. You mentioned that you had a
I think it was, I was wondering if this data are sort of biased towards people that are more on the road, this EMS data.
So, well, the idea,
Or it's also people calling from home.
so people can have emergencies anywhere and they call from where they are. And the hope is that the way these emergencies occur is sort of uncorrelated with people's, activity patterns, but that's not strictly true.
Yeah.
Because, when you're at home and you're relaxed and, sleeping, nothing goes wrong very much. But when you're out and you're stressed or exposed to something, then more things happen. But in a way, that's okay, because what we're trying to capture is the dynamic nature of vulnerability. So if bad things happen while you're out and about more than they happen at home, then we need to capture that in order to understand vulnerability properly.
There's a question online as well. And Tabia, can you just unmute yourself?
Sure. Thanks a lot for this really interesting talk. So I actually have two questions. One is about this disaster simulations. Unfortunately, a lot of the environmental disasters happen in the global south, in rather regions that they do not regularly have access to very high quality data, for example. about geographic data. So a lot of it can be, of course, compensated by remote sensing, but also like the geographic data on the population particularly. Do you think, and behavior as well, do you think, for example, that some of these model components that can be calibrated on with data from places where it's available is generalizable and can be therefore, used? So, for example, these behavioral models, can they be used in, for example, places in the global south which really need a lot of disaster models as well?
That's an excellent question. I have a multi-part response to that. One is we are trying to build synthetic population models for the whole world. They're, of course, coarser than, for example, what we can manage for the United States, because, like you said, the quality of the data isn't the same. But still, having even a coarse representation of the population, I think, is very useful for enabling these kinds of models. So that's one. The other is there are some kinds of data that we can get globally now. You can get remote sensing, of course, but you can also get mobility data or location data. That was the picture I showed earlier from a mobility company that has global data, and it has actually, surprisingly good coverage. Not everywhere, but if we go back to that. So if we go back to this picture, you can see, of course, the coverage is much denser in the US and in Europe, but India has pretty dense coverage. Southeast Asia, South Africa, Brazil, the west coast of South America. So there's actually good quality data starting to be available. And I think it's an open question how to best make use of these kinds of data. But I think in a way, we're living in exciting times. Not only are there global level disasters happening, but we are also getting the tools and the data to be able to address these challenges. And the third thing is that in the work I showed, there are actually multiple pieces. So maybe you can't build a very detailed agent-based simulation for some parts of the world, which is completely understandable. I mean, we had to deal with this when there was the Ebola outbreak, which was in Western Africa, and this was in 2014. And of the 3 countries that were affected, Guinea, Liberia, and Sierra Leone, I think Liberia was the only one that even had a recent census. That census was from 2008. The other 2 countries, the last census was in like the 1970s, right? So just the data quality just wasn't there. It was terrible, right? So we have to do something. We end up making some coarser models, like differential equation models and so forth. But what we're finding is that there are more and more efforts at data gathering in many parts of the world that, while they may not support full-fledged agent-based models with the level of detail that I showed here, they do support new approaches like machine learning-based approaches to calculate vulnerability indices, for example, that are driven by health outcomes.
Really interesting, thanks. I don't know if I can still ask a small second question, which is also about the synthetic agent population, actually. There was one mentioned about Virginia, I think, in the beginning. And there was also a mentioning of network analysis. And I was wondering if this synthetic agent population is basically a database of individuals with attributes, or if it's even a network database of social networks, for example, with nested household structures and relations based on family relations or something like that, because that is much harder to find or also to generate based on the type of statistics that are commonly available, publicly available.
Yeah, so it is in fact all of those. So this cartoon sort of illustrates it. We start with information about demographics, but then we add in information about, so the demographics actually come with household structure in the US Census, so we have that. But then we add in information about activity patterns. So we assign reasonable weekly activity patterns to these people, like going to work or going to school or going to shopping or home or things like that. And then we have very detailed location information. So where workplaces are, where schools are, and so forth. And so where people go and where they might interact with each other, so we can extract a network from it.
Oh, yeah.
So it's very detailed, and we've spent a lot of time in building out the methodology for these. And I'd be happy to point you to a write-up or even a tutorial on what's there in our synthetic populations.
Yeah, great. That would be nice. Thanks.
It's a simple question. First is about the uncertainty of not of the model itself, but of the disaster event. Duration, timing, path, or so on. Like how robust are the outcomes to those changes? And secondly, what does this tell us about? What does this tell us about Harvey that we wouldn't have known before, or equally for similar sized and disaster later? What we learned from this?
Right. So sensitivity analysis and uncertainty quantification are very much open questions. So the short answer is there's not much I can tell you right now about how some changes to these events would affect the vulnerability. It's something we would have to compute. And that's precisely the reason for building these simulations, to be able to compute those outcomes. Right? But we have the tools now that we could say that what if the rainfall had been less, or it had been in a slightly different area, the flooding had been a little different, how would that have changed things? How sensitive is our measure of vulnerability here to small changes in those kinds of details, right? So we haven't done that yet, but it is now possible. As to what can we learn from this that is generalizable, I think that the important thing is that it's the methodology development, right? So every hurricane is different. And in fact, people's responses are different in every hurricane because they learn from previous exposures, right? People's responses are different in every pandemic. They learn from previous pandemics, right? So it's with complex social systems, it's actually very hard to generalize. And it's really important to have the right data and the right methods to be able to do any kind of even broad prediction. Yeah.
Yes. So my question is about the synthetic population and the uncertainty in it. Because I can expect that people don't behave rationally as a modeler would predict. So how much does that affect, let's say, with your validation, or have you ever faced situations where you start off with a set of rules for the population and then have to change it later to a very different set of rules just because you can't really match the data that you see?
So it's a complicated question, and so there's, about one question is about the uncertainty in the structure of the synthetic population. The other is uncertainty about human behavior in events like hurricanes or other disasters, right? And so we do a lot of effort, we put a lot of effort into understanding the statistical rigor of or how that matches the real data for the synthetic population. And some steps there, actually, the methods we use have some kind of theoretical guarantees. Like the very first step where we synthesize the agents with the demographics, we use something called iterative proportional fitting, which has the maximum entropy interpretation. So it's like, given the information you have, you're coming up with a maximum entropy estimate of the joint distribution over some variables, right? So in that sense, it's rigorous. But then when we come to each step in the population, as we're layering in more data, it can turn out that you added information about activities and everything was fine, and then you try to add information about where people go to do these activities. And suddenly, so there's some inconsistency which requires you to go back and change the activity assignment you did, right? So that can happen. It's not just a feed-forward process where you keep layering in more data. You have to adjust things that you might have done earlier to ensure consistency of what you produce. So yeah, it's complicated, is the short answer, but we are aware of that, and we try our best to validate at every step of the process. The human behavior part, that's very much an exciting frontier for this research. That's the kind of thing we're working on together too, with putting in BDI models and more rigorous forms of modeling social reasoning and so forth. I think for me personally, that's the most interesting direction in which this research is headed.